Okay, today I'm going to go over the recitation group work. This primarily covers chapter 13. Here, let me get this situated a little bit better. Okay, so we're going to start with defining terms: conjugated, isolated, cumulated, homo, and lumo. This is referring to like double bonds for all three of the conjugated, isolated, and cumulated. And conjugated is a double bond adjacent to a pi orbital that can be in resonance. So I think of it, like if you have alternating double bonds, that's conjugated. Isolated is if you have isolated double bonds. So they're not alternating double bonds. They don't have a chain of p orbitals available. Like here, there's a whole chain of p orbitals. Down here, the chain is blocked. And the way I know that there are p orbitals on these is the hybridization. So if you have something that's sp3 hybrid, like all these alkanes are sp3 hybridized, all the three p orbitals that atoms have access to are totally used up, right? All three of them are used up. But if you have a double bond, that's sp2 hybridized, right? So there's a p orbital that's not being used in that hybrid system that is instead being used to hold that double bond. And if you have a carbocation, that's also sp2 hybridized. So there is a p orbital available here as well. Same thing if you have a carbanion, those are held in a p orbital. You'll see in chapter 15 they can kind of go back and forth, but they're usually held in a p orbital. And then radicals are also held in a p orbital. So that's what we mean when we have like a conjugated pi system, is it has p orbitals all adjacent to each other. It creates like an electron highway where there's resonance all among those. But isolated, there's a break in the p orbital highway. And then cumulated is like for cumulines, if you have two carbon double bonds. We don't talk about those a lot. These are actually interesting because they're stereocenters but like right here is a stereocenter. This is like a chiral molecule. But we don't talk about that a ton. And then homo and lumo is if you have atomic orbitals like an s orbital from a hydrogen and an s orbital from a carbon, they combine and make molecular orbitals. So like if you have the individual orbitals, they combine to make the molecular orbitals. And you also see this with p orbitals or whatever. I think of them as rungs on an energy ladder. And as you go up the energy ladder, you'll have electrons fill in. And these lower electrons right here, when energy goes in, they'll be excited up to the higher electrons. And the difference here in this wavelength, the difference between these energy levels, is the energy that is absorbed whenever energy is put in. Energy absorbed when irradiated with light or some other type of energy. And when that happens, this specific amount of energy goes in. And that's the difference between the HOMO and the LUMO. Sometimes they'll jump extra high, but pretty much you'll see just like an excitation to the next energy level. And that energy level is connected to wavelength. So those are your HOMO and LUMO. This is the highest occupied molecular orbital. Highest occupied molecular orbital, HOMO, and then this would be your lowest unoccupied molecular orbital. There was a test question that I think it was Dr. Berhe used to ask, where he would ask students how many electrons are in the LUMO, and you would just only need to know the definition, because if it's the lowest unoccupied, the answer to that question is always 0. So I really like that question. Okay, so the next question is explain why conjugated molecules can absorb radiation in the UV-Vis spectrum. So really, I think the best answer for this is that the amount of energy between the HOMO and the LUMO that's absorbed when electrons get excited is in that UV-vis spectrum. But the reason it's in that spectrum is this energy level is lower, which corresponds to a higher wavelength, and that is in the visible region. So essentially, the conjugation allows a lower level of energy to be absorbed, which happens to be in the visible region. I feel like this is kind of one of those answers that's like, it just so happens that it absorbs the right amount of energy to be in that area of the electromagnetic spectrum. But it is a lower energy gap between the conjugated systems because it's stabilized by resonance. So that is another reason. But yeah, that's how I would kind of summarize it, is it's this perfect energy level to absorb in the visible region. That energy level happens to be lower. The energy that needs to be absorbed happens to be lower, and it corresponds to a higher wavelength. And that's also the answer to the next question. So lambda max is actually wavelength, and I think you'll learn more about this in I learned about this in quant and instrumental analysis. So if you go on in more chemistry or physics, you'll learn more about this. But lambda max is wavelength, and if you have a lower energy, you'll have a higher wavelength. So the more conjugated bonds, more stable, lower energy, higher wavelength. So really it's because resonance stabilizes making a lower energy transition when the light absorbs. So basically the energy is put into your molecule, off camera, energy is put into your molecule, that energy is absorbed in this specific wavelength, and it happens to be a lower wavelength that's absorbed because of the conjugation and the resonance. And then that lower energy corresponds to a higher wavelength. Did I say that right? Energy is put in, lower energy due to the resonance stabilization gives you a higher wavelength. I always get those kind of mixed up, so I always have to write down lower energy is higher wavelength, just because it always gets me mixed up. I think that's kind of I kind of get tongue twisted on that concept, but that is responsible for so many things. So chlorophyll has highly conjugated systems, blueberries, the things that make blueberries blue are highly conjugated. Chlorophyll is what makes plants green. Anthocyanins are the class of molecules that make cyanins. I spelled that wrong, I think. Are they that make trees red in the fall, as the chlorophyll fades away? So to be able to see anthocyanins, that's a highly conjugated molecule. In cabbage and carrots, and in Dr. Cross talked about in class today, the genes, your dye in your genes, all those things are really highly conjugated systems. I'm looking at this, I got this cute journal. This, whatever was used to make this green was a highly conjugated system. So anything that is going to be highly colored comes from a highly conjugated system. I feel like we could make this light situation better. I always feel like that, I think. Let's see. There we go. Maybe that's better. I don't know. I guess we'll see. Okay. It looks so bright in front of me, but so dark on the camera, which is weird. Okay, this is one I'm excited to talk about. So, one thing that I think is important with mechanisms is we organic chemists, I don't do this kind of research anymore, but organic chemists do research mechanisms of reactions, and will run experiments to determine which mechanisms are most likely to occur. But we don't know everything yet. There's conversations about what's happening. And Dr. Cross and I had a conversation today where we think at lower temperatures, this may go by the carbocation mechanism, or it may go by brominium ion mechanism. I don't think anyone knows for sure, but it will still go through the 1,2,1,4 addition. So first I'm just going to say what I mean by 1,2,1,4 addition. So 1, 2, 3, 4 carbons on this molecule. When you have something like Br2, there we go. When you have something like Br2 or HBr, basically something that has an electrophilic and nucleophilic side, it can either add 1, 2, so HBr, or it can add 1, 4, HBr, like that. And the mechanism we typically know is the carbocation mechanism. So that's responsible for this 1, 2, 1, 4 addition. So if you have HBr, this will attack, this bond will break, and you'll end up with a carbocation, and it's going to be the most stable carbocation, just like we learned in Markovnikov's rule. Whatever's going to give you the most stable carbocation, the hydrogen's going to add on the opposite side than that. So from here, you can go one of two ways. Either your bromine can attack at that carbocation, and you end up with the 1, 2 addition, HBr, or this what is that called? This double bond moves over in a resonance structure, right? And your carbocation is more highly concentrated on this side. So the hydrogen was still added over here. That hasn't changed. That's the 1 addition. But then your bromine can attack the carbocation on this side, giving you the 1, 4 addition. 1, 4 addition is harder to get. So you need a higher temperature to achieve that. It's obviously harder to get because there's more steps, right? This one over here, it happens really quick. This one, you have the whole resonance structure take place. So that's how I remember. It's harder to get, so you need higher temperature. So this is known as being under kinetic control, the 1, 4. And then this is thermodynamic, I think. Let me make sure. I don't want to say the wrong thing. Okay, I went and stopped and checked because as soon as I said it, I was like, wait, I'm not 100% sure that's correct. So I actually did get it backwards. This one is harder to get. It requires more energy to put in to get it, but it does give you the more stable product. Because, and you can think of that, obviously, because you know double bonds internally are more stable. So 1, 4 is more stable, and that is the thermodynamic product. And then the 1, 2 addition is actually known as the kinetic product. So I mixed those up. I got those backwards. So sorry about that. I always want to make sure I immediately catch it. And as soon as I said it, I was like, wait, I tend to get those mixed up. Let me double check. So then the other thing I wanted to talk about is this is the way we normally know the carbocation method. It's possible that this mechanism works for the Br2 at low temperatures, but also I want us to talk about there's a proposed reaction mechanism that does include the bromonium ion. So whichever one of these makes more sense to you to think about, you can think about it that way. Either way, I'm fine with it. So the first step is the same. This would attack the bromine. If it was Br2, this would attack the bromine, this bond would break, and you'd end up with this brominium ion that forms. So we talked all about the formation of the brominium ion in bromonium ion in chapter 8 with addition reactions. And then your nucleophile, normally, again, you can go one of two ways. Normally, your nucleophile would attack on the internal side, it's Markovnikov, and you'd get a 1, 2 addition of bromine. The other option is for this bromine to attack here on the outside edge. This bond to come in the middle, and then there'd be too many bonds to this carbon, so this bond would break. And you'd still get an addition at the 1 position, but the other one attacked at 4. So these are the 2 different mechanisms that you could get. Either you could have the bromonium or you could have the carbocation. I think either of these is going to be fine. Either of these will be accepted by Dr. Corrales and I on your exams. Okay, so Okay, now which of these products would be favored if the reaction is conducted at a higher temperature? So higher temperature means they're going to be able to put more energy in, and it'll get to the more stable product over time. So the more stable product, this is the thermodynamically controlled, and you get the 1,4 addition. So if you're doing HBr, it would be this, or if you're adding the 2 bromines, it would be this. Then if you do this at low temperature, the easier thing would happen first, the easier reaction would occur. And so the 1,2 predominates because you don't need as much energy to get the 1,2 addition. So that would be either HBr or Br at the 1,2. So sorry, I kind of mixed this up earlier, but this is correct now. This one's the right one. I should always check my notes before I speak. Okay. Now let's move on to question 4. This is just a bunch of reaction mechanisms. So the first one is another one of these. You would have the, just like a regular addition reaction, the alkene would attack the H and the bromine would break. And if you're not sure what kind of reaction is going to take place, I always just run down the list of what are all the reactions we know. And now that we've worked some on chapter, I'm trying to get this camera to not have such a shadow. Now that we've worked some on chapter 12, we can add into that. We have our acid-base reaction, our substitution or elimination reaction for chapter 6 and 7. Chapter 8, we learned addition reactions. 10, we learned radical reactions. And then 11, we did reactions of alcohols and epoxides, alcohols and ethers. And then for 12, we did oxidation reduction. And now we have conjugation, conjugated reactions, conjugated addition reactions, so 1,4. And then we'll learn one other type of reaction for this chapter called a Diels-Alder. So I'm going to run down this thing, and this could be an addition reaction, but because I see conjugation, I know that's going to be a 1,2 or 1,4 addition, so that's how I knew to go for this. And the initial addition, if we get the kinetic product, would be a Br here and a hydrogen there, a 1,2 addition. The alternative option is, actually I'll do this in a different color. This electron comes in and attacks, and then you get, or this, the bonds from the electrons in this double bond, sorry, it's late at night and I always misspeak as I get more tired, move over and form a carbocation over here. The hydrogen has still added in at this position, at position 1, but then the bromine can attack at position 4. So in blue, you have the 1,4 addition, and in black, you have the 1,2 addition. Oh, I added in, I lost a methyl group right there. So these are your 1,2 and 1,4 possible products. Now this next reaction, this is just a radical reaction, and I actually am going to be posting a video today regarding radical reactions. Basically, they have the initiation step, propagation, and termination. So this will generate a radical. When you have NBS, it is especially good at generating bromine radicals. So we'll say it generates 2 bromine radicals. And then that bromine will scavenge for the most stable position. So it sees this hydrogen is stable, and it's going to take one of the electrons. Sorry, that should be a single barb. It's going to take one of the electrons from the hydrogen and one electron from the bromine, and it's going to form HBr. There will still be this bromine radical, but it leaves behind a radical on the original molecule. And the reason that this was the most stable position for a radical to form is for 2 reasons. One, it's secondary. So that's more stable than primary, either of these positions over here. But 2, it's allylic, so it has resonance structures. So it's important for you to be able to draw resonance structures of radicals. The one electron would move from this double bond and one from the radical, and you have this as a resonance structure. Or if we go the other side, I'll again draw it in blue, the radical here, and one electron from that double bond, and you'd get this as a resonance structure. So either one of those is valid resonance structures. They'll contribute less to the overall hybrid because they are primary, but they will contribute. So those resonance structures make that middle position, that allylic position, more stable. So that's the initiation. Then you get the propagation step that leaves a radical behind, and then termination where this reacts with the bromine, and you'll get a bromine right here. So that's the whole mechanism. Sorry, I'm a little bit off camera. That's the whole mechanism for this reaction. Really, all you need to know is it's going to form a radical at the most stable position for a radical, and then it's going to add a bromine or a chlorine or whatever right there. And I do want to say, in terms of radicals, resonance are the most stable. Then if you have a tertiary, then secondary, and primaries don't really happen. But like if you have a tertiary with resonance, that's better than a plain old tertiary. I don't know how a tertiary could have resonance, but you know what I mean. Or a secondary with resonance, that's better than just a plain old secondary. Resonance always makes things better. Okay, now draw the mechanism of the following reaction. This is just another radical reaction. So this chlorine will actually break. In the initiation step, you get 2 chlorine radicals formed. And the reason I know that this is a radical reaction is going down our list. It's not acid-base. There's no H+, there's no base. That doesn't make sense. There's no good leaving group. It's the chlorine can't act as a leaving group or a nucleophile. It doesn't seem to be an addition reaction because of the heat. So if this was just Cl2 and like CCl4, it would add a chlorine. It would go like a chlorinium ion and add a chlorine at the 1,2 position as an addition reaction. But because there's heat or light, that makes it a radical reaction. So you have to know what to look for to see each of these different reactions. So this extreme heat, 400 degrees Celsius, that's 4 times the boiling point of water. Like that is really hot. So that is going to create a radical, the initiation step. And then now with chlorine, is less selective than bromine, but it still likely will form a stable radical right here. So it takes a hydrogen to form this stable radical, and then I guess I can go ahead and draw that step in for you. I want you to be able to see while I'm writing, but can't quite get my camera angle good today. So one of these chlorines will come and take an electron from this bond between the hydrogen, leaving behind a radical. And then the other chlorine will combine with that radical, and you'll get an addition of chlorine. It will likely add in other places too, because chlorine radicals are more reactive than bromine and less selective, but I usually go for the most stable position on both of those. Okay. Now again, Br2, Dr. Carlos told me this is supposed to have light or heat either way. I know it's not an addition reaction because it doesn't have a double bond, not an acid base, not a substitution or elimination. The only thing left it could be would be a radical reaction. So the first step, initiation, that light is going to break up your bromine radical, break up your bromine into 2 radicals, and then it will take a hydrogen from the most stable position. So there's not a hydrogen here. All these are primaries. That's a secondary. That is a tertiary. So that's going to be the most stable position. So one of these bromines is going to take an electron from there. The other one's going to leave it behind. Let's see. And you get a radical formed. And then this bromine will combine with that. That bromine radical will combine with that radical to get you a bromine added in there. And if you don't have all those steps memorized, you can just remember the radical forms at the most stable position, and that's where the bromine goes. Now, when I see Cl2 and CCl4, there's no heat or light to form that initiation step in the radical reaction. So I think this is actually an addition reaction. It's not an acid base. There's no good leaving group for substitution or elimination. The next thing we learned about was addition reaction. And so I think that this will form, we'll just draw that out, a chlorinium ion, similar to the brominium ion that we talked about earlier. And then the other chlorine will come in and attack and kick that out. And you'll get 2 chlorines, so 1,2 addition of chlorine. There's not a 1,4 possibility because that's not a double bond right there. Now the next question, so similar, this helps you see the difference between addition and radical reactions, but there is an initiator, so that makes it a radical reaction. So the first step is we form our chlorine, then the radical is going to form after the hydrogen abstracts from the most stable position. And I want you to ask yourself, do you know why that's the most stable position? And I really hope you do. It's because it's the allylic position, which means there's a resonance structure. So at this position right there, you can form a resonance structure. So even though maybe there's another secondary position, it's on a double bond, it doesn't have resonance, so this is better. So this is the most stable position, and your chlorine would go there. But remember, chlorine is more reactive than bromine radicals, so it could also go to the primary positions as well, because chlorine is crazy. Okay, NBS is the same thing. NBS with an initiator makes bromine radicals. Now, this is a good question because you could make a radical. There's 2 allylic positions, right? There's one here or here. These are very, very similar. But there is one thing that you can look at to see which one is more stable, and that is what resonance structure it would form. So here, the resonance structure would be on a tertiary, right? These 2 are in resonance with each other. And if you go to the other side, this resonance structure forms over here on a secondary. So actually this one is more stable because of that. That's kind of an advanced idea. So if you didn't get that, that's a-okay. I'm not going to be upset. I think you might want to have that down by the test. But for now, if you didn't get that, that's okay. But that makes me think that this right here is the most stable position. So that's where the bromine's going to abstract the hydrogen from, leaving behind a radical. And that's where your bromine will attach. So that is the answer. If you put a bromine over here too, like you're getting it, you're close. I don't think anyone's going to be mad at you, but I do want you to start thinking of that next level. How can I tell how stable this radical is going to be? So many radical reactions. Okay, so these 2 are both radical reactions, and we know because there's NBS, right? So that definitely makes it easier for us that we see the NBS. We just have to pick the most stable radical. In this case, there's symmetry right through the middle, so either of the allylic positions is going to give you the same thing. So that's the most stable position for the radical to form, so that's where the bromine's going to go. For NBS, I like this one because this brings attention to a different position that we haven't talked about, which is benzylic. So we've talked about allylic a lot, but a benzylic position is very similar in that you have resonance structures actually that go all the way around the ring. So this radical is even more stable than the allylic radical, but for similar reasons. So if that's where the most stable radical can form, then that's where the bromine would go. Okay, and then, this next question is a little bit different. There is a peroxide with an initiator. So this is actually, though, an addition reaction, and that's kind of confusing. It's an addition reaction that goes by a radical mechanism. So normally, if you didn't have these 2 and you had HBr, the first step would be this attacks the hydrogen, this bond breaks, the hydrogen is added, and the most stable carbocation is formed. and then the Br minus comes in and attacks, and you get a Markovnikov addition of bromine across a double bond, right? Well, if you have a radical and an initiator, you actually just get the opposite. You get an anti-Markovnikov addition of bromine and hydrogen. And I go over the mechanism for that in chapter 10. You're not required to know it. I think it's helpful, so you can go back and check out those practice problems if you want. But basically, a radical forms with the H and the Br, and then the H abstracts the radical, or the Br. I don't remember it exactly. You'll have to go back and look. I don't have it on the top of my mind. But just all you have to remember is this makes the anti-Markovnikov addition reaction via a radical mechanism. And we talk about that in chapter 10. Okay. Also, just to warn you before we start on this question on the back, my husband is making tea. So if you hear the sound of boiling water, that's his sleepy time tea getting ready to go. So it's nighttime, you know. Sometimes you got to do what you got to do. Okay, so for this next question, we're trying to determine how to synthesize 1,3-butadiene from all these different starting materials. So basically this. Now, when I see how do you make a double bond, I'm immediately thinking this is an elimination reaction question, except for this one that starts with a triple bond. So that's where I'm coming from. And I like 1,4-dibromobutane because these are both, did I add this? No, that's 1,3. I'm going to draw out 1, 2, 3, 4 dibromo, because that's going to be a really good leaving group, right? So I see that. I'm like, this is going to be an E2 reaction. I've got a good leaving group on a primary thing. I just need heat and a bulky nucleophile. So if I do that times 2, this could be an E2 reaction. So that's what I'm going to go, E2 with tert butoxide and heat to get 2 elimination reactions to go from this to this. So the mechanism on that would be, let's see, if we have this, my big bulky nucleophile is going to come. It's going to take a hydrogen from here. The electrons will be left behind, and the leaving group will leave, and it will repeat that twice. So that goes all the way back to chapter 6. I see this one, and I'm thinking all I need is to add PBr3 to what we did from step A and turn these alcohols into bromines. Now, I could protonate this and try to do an acid-catalyzed elimination, but that would require the formation of a primary carbocation, so that's not going to work as well. So I actually like this mechanism better. And I'm going to do the same thing on part C. We only have to eliminate one thing, so I would use PBr3. Oh, I don't even know what I was spelling there. PBr3, and then the same thing. What we did in part A, a big bulky nucleophile and heat to encourage an elimination reaction. Part D is very similar to part C. We don't even have to convert it to a good leaving group. We just need our big nucleophile and heat to encourage an E2 reaction. So these are all very similar. If you have other ideas about how you would do this reaction, it's possible that they would work. You just need to make sure you know exactly what it is you're doing so that you make sure that it would accomplish the goal that you think it will. So like if you're not sure and you want to check with me, you can just email me or whatever. And then for this one, I would actually probably go with an E1 reaction with a weaker nucleophile and heat, just because the leaving group leaving would give a carbocation just to mix things up. But you probably could also do an E2 on this, but you know with secondary leaving groups, E2, you know, it's going to also compete. So that's what I would do for that one. And on this one, I would actually probably do acid catalyzed dehydration. Again, an E1 reaction, OH2 plus, the leaving group would leave. And on this very last one, this is a triple bond. So to get a triple bond to a double bond, I have this stair-step analogy where it's like if you have a triple bond, it's going to go a second double bond and then a single bond, like alkyne to alkene to alkane really quickly. Like it's somebody walking downstairs. You don't stop midway down the stairs unless there's a reason. And so we actually have Lindlar's catalyst as a good reason, which is also known as a poisoned catalyst. And it will force your triple bond to only get reduced down to a double bond. And we learned about that with, it's like H2, P2 is a poison catalyst, and it'll take you from a triple bond to a double bond. There's also dissolving metal reduction and what's the other one? Dissolving metal reduction and quinoline. There's like something with quinoline that will do it. So for all these, you basically just need to engineer your own, all the rest of them, you basically just need to engineer your own elimination reaction. Whatever works the best for you is fine. Yeah, those should work well. Okay, and then very last question, predict the major product of the reaction sequence. So we know PBr3 turns primary and secondary alcohols into a bromine. And then if you add MgBr, that's basically the equivalent of these two carbons with a negative charge and then this with a positive charge. So I just draw it out like that. And it's probably going to do an SN2 reaction, which I know because that would be a strong nucleophile, and that's a good leaving group. So that's how I conclude that. And then that must mean a bond forms between these two carbons. And now with substitution elimination reactions, a lot of times I lose count. So I'm going to number this. 1, 2, 3, 4. So there was a bond between 4 and bromine, but now there needs to be a bond between 4, 5, and 6. So 1, 2, 3, 4, 5, 6. Okay, that looks good. Okay, so I think that would be your the result of part 2. This H3O plus just neutralizes whatever's left over in solution from your Grignard reagent. And then if you add Br2 and light is an initiator, so hopefully you recognize that makes a radical reaction. And a radical reaction forms the most stable radical. And then you combine that with a Br radical, and you get a radical on your alkane. All right, well, I hope that was helpful to y'all. If you have any questions or you want me to go more in depth on anything, just let me know. Happy studying.